Okay, so to prove the part A, we've got, let's just start on our left-hand side and see how we go. So if our left-hand side, and we're going to struggle here with my writing, is equal to cos alpha minus cos alpha plus 2 beta, all on 2 sine beta. All right. So cos alpha is all nice and fine. If we expand cos alpha plus beta, so this is plus 2 beta, this is compound angle. So you can tell that we are going to get cos A cos B. So in this case, cos alpha cos 2 beta. And remember it's a minus, so sine alpha sine 2 beta. All right, and that's all on 2 sine beta. All right. And then, of course, we need to expand our double angles because if you look at our answer, it's only got a single angles in it. So if I have cos alpha, and also on the right-hand side is in terms of sine, so I'll put everything in terms of sine. So we know that cos 2b is the same as cos squared beta, cos squared beta minus sine squared beta. So that's the same as 1 minus 2 sine squared beta as well. So I'll just put that here, 1 minus 2 sine squared beta is cos 2 beta. And then we've got this minus minus, so I'm going to make that a plus. And we've got sine alpha, and we know that sine 2 beta is 2 sine beta cos beta. I'll just put that here, 2 sine beta cos beta, all over 2 sine beta. All right, so run out of room. If I go here, so now if I just put those first two terms together, so there's a cos alpha, you can see there's this one, minus this other stuff. So it's minus 1 minus 2 sine squared betas. And if I rearrange this one, I've got 2. I'll just put 2 at the front. I've got sine alpha, sine beta, and cos beta. Still all over 2 sine beta. All right, so now you can see we have a 1 minus a 1, so that's a 0, and a minus minus is a positive, so it's got a 2 sine squared beta cos alpha. So 2 sine squared beta times by that cos alpha. All right, and this is all still here. You can see that now we can cancel. I should have factorized, but anyway, if I factorize the top by 2 sine beta, 2 sine beta, you can see we're still going to have this sine beta cos alpha and 2 sine beta, so this is going to be sine alpha cos beta, all on our 2 sine beta. So you can see now that this will cancel. I'll just do it over here, and we're left with that compound angle expansion of our sine alpha plus beta, which is what hopefully we were looking for. There we go. So what we can do is we can use that, or we should use that, in our second part. So yeah, so hopefully you've really got your trig going from year 11, and you're practicing it and revising it all the time. So we're going to use it here. I'm going to skip a few steps. So, of course, we need the proposition. So let P of n represent the proposition. This is the proposition. We're going to have a base case. So, for example, when n equals 1, we've got just sine theta. So we will have this. We'll have sine theta on one side, and on this side we'll have 1 minus cos 2 theta on sine 2 theta. 1 minus cos 2 theta on 2 sine theta, and it has to equal sine theta. So we would expand out again. So 1 minus, cos 2 theta is 1 minus sine squared theta. So maybe we could do that. And let's see what we get. Whoops. Cos 2 theta is 1 minus 2. Where's my 2 gone? There's my 2. All right, so we get a 1 minus a 1 and a plus 2 sine squared theta when we expand that out on 2 sine theta. So you can see that we will get sine theta. So it does work for the base case. Worth a check there. All right, so it works for the base case. The next case we would assume true. Remember that sine theta plus sine 3 theta all the way up to sine 2k minus 1 thetas is equal to 1 minus cos 2k thetas on 2 sine thetas. All right, and we're required to prove that, the p of k plus 1. All right, I don't know why I'm writing that and it's so messy, sorry. All right, so if I write that sine theta plus sine 3 theta, we're going to go, so it's all these ones, all the way up to that one, and then we're going to add on another one. So we've also got sine of, if you think of putting k plus 1 in here, we will get the 2k, we'll also get a plus 2 minus 1, so it's a plus 1 theta. All right, and we have to show that that is going to equal 1 minus cos. Now, we've got 2k plus 1 thetas, 2k plus 1 thetas there on 2 sine theta. So 2 lots of k plus 1, so 2 times k plus 1 times theta. All right, so let's look at the left-hand side. And you can see that the first few terms, so from sine theta up to our sine 2k minus 1 theta, that's all just from our proposition k. And then we're going to add on the last term, which was the 2k minus, plus 1 theta. There we go. All right, so if we use from our p of k, we've got 1 minus cos 2k theta over 2 sine theta. Plus, we've got sine of 2k plus 1 thetas. Alrighty, so what we're going to do is use our, so that's from p of k, I really should write that, from p of k. And what we're going to now use is our part A. So you can see here we've got, if I was breaking up this sign here into two, it would be 2k theta and theta, and theta. 2k theta and theta. All right, that would be another way to write it. So if we make alpha 2k theta and beta theta, what does that equal? Beta theta. All right, so we've still got this bit, so we'll keep that there. And this bit here we're going to use, so remember alpha is 2k theta, so we're going to have cos 2k thetas minus cos, we're going to have alpha, which is 2k theta, plus 2 lots of beta, and beta is theta, so 2 lots of thetas, and it's all on 2 sine beta, and remember beta is theta. All right, try and keep that in your head. All right, so now it looks good because remember this is what we're aiming for, and we've now got a common denominator of 2 sine theta, very handy. And we've got 1 minus cos 2k theta from the first fraction. The second one we've got plus cos 2k theta. So those 2k thetas, you think about it, they're going to cancel. Minus, all right, so we've got cos here. We've got minus, I want that, don't I? So keep that, sorry, 2, so minus cos, and these have both got 2 and theta in them. They've got a 2 and a theta, and so that would be a k plus 1 left if I were to factorize. And you can see that's the same as, so once these two cancel, I'm just going to fit it over here. I've got 1 minus cos, so it's the same as writing the 2 and the k plus 1 second and then the theta, which is the same as here, 2k plus 1 theta on 2 sine theta. So it does equal the right-hand side, therefore p of k implies p of k plus 1, and then therefore it's true for Pn, but Pn is true, so it's true for all n is greater or equal to 1. All right, hope that helps.